Hi everyone, and welcome back. Today we'll start chapter 6, in which we'll learn how to formulate gauge theories with a non-abelian gauge group. And we'll do that following Chen-Ning Yang and Robert Mills, who developed the modern formulation of gauge theories in 1954, and in particular applied it to the general setting of non-abelian gauge groups. This is important because non-abelian gauge theories are everywhere in modern physics, in particular the language of the standard model of particle physics. And also, as we'll see later in the term, they build a very useful bridge between physics and mathematics. So as it turns out, the study of non-abelian gauge theories has led to many developments in both subjects, including quite a few Nobel Prizes and Fields Medals. We'll spend the rest of the term studying the geometry and also some topology, which underlies non-abelian gauge field configurations. But before we do that, we need to go through the formulation of non-abelian gauge theories. And in this chapter, we'll take more of the physical route. We'll go to the mathematics later. And we'll start today by introducing the cast of characters of these non-abelian gauge theories, which consists of compact Lie groups, compact Lie algebras, and their representations. I'll start with section 6.1 today, which is about compact Lie algebras, although I'll say also a few words about the associated compact Lie groups. So what we'll do today is mostly a review of material from term 1 again, but I'll introduce some different conventions, slightly different conventions, which are widely used in the physics literature. This to set the stage for Friday's lecture, in which we'll use these ingredients to formulate non-abelian gauge theories. All right, let's start by recalling the notion of a Lie algebra. The Lie algebra, which I'll denote as G. This is meant to be some calligraphic lowercase g. A Lie algebra is a vector space, and we'll use finite dimensional vector spaces throughout, with an additional structure the so-called Lie bracket, an antisymmetric form, which takes two elements of the Lie algebra and maps it to another element of the Lie algebra. The Lie algebra is a vector space, so there will be a basis. And let's call the basis vectors TA. A runs from 1 to the dimension of the Lie algebra. And typically, the basis elements of the Lie algebra are called generators of the Lie algebra. And we specify the Lie bracket by its action on the generator. So the Lie bracket, say, of two generators TA and TB must be an element of the Lie algebra, so it has to be expressible as a linear combination of the generators. And this linear combination is FABC times TC, where here A, B, C again run from 1 to the dimension of the Lie algebra. And FABC which are antisymmetric in the indices A and B, because the Lie bracket is antisymmetric, are real structure constants. So far, I believe that everything is as you've seen it with Andreas. And now I'll introduce the first change of convention, which is typical in the physics literature. I'll stick an I in the right-hand side, where I here is a square root of -1. And I'll return y that might be useful in a few minutes. The Lie bracket is bilinear antisymmetric, and it further obeys the so-called Jacobi identity. Which states that if we take the commutator of two elements of the Lie algebra, and here I'll apply it to the generator, so the bracket of T A, T B, and then we take the bracket of that with the TC, and finally we add the cyclic permutations. We'll have TB Lie bracket with TC, all Lie bracket with TA, plus TC Lie bracket with TA, all the bracket with TB. So this, in terms of the structure constant, implies the following version of the Jacobi identity, that FAB DFDC E plus cyclic permutations of the ABC indices, so FBC D FDA E plus FCA DF DB E is equal to 0. If you haven't done this exercise before, please check that 6.2 implies 6.3. Then we introduce the notion of representation of the Lie algebra. And in particular, we say that an R-dimensional representation, from now on I'll write simply rep, of the Lie algebra G is a realization of the generators TA as a set of R times R matrices satisfying the Lie bracket 6.1, where now in the representation, so in this matrix realization, the Lie bracket becomes the commutator of matrices. So the commutator of A and B is AB minus BA. And a notation that we'll often use, so sometimes denote the representation by R with an underscore when I write here, and possibly in the lecture notes I'll use boldface. It might be the case that there are multiple representations with the same dimension R, and in that case I'll adapt the notation. More about this, for instance, later today. For instance, we'll have I don't know, R, R prime, etc. But I'll use R for the representations, and for the generators of the representations, I'll typically write TA with a parenthesis R in the subscript to denote that these are the generators in the representation R. If it's clear from the context which representation we will be talking about, and this will be clear in particular later on when we discuss and use the fundamental and the adjoint representation, I might omit specifying which representation we are talking about, but otherwise and certainly today I'll try to be explicit about which representation we're talking about. In the context of gauge theories, we are actually interested not in any Lie algebras, but in compact Lie algebras. The reason will be that we want the kinetic terms for the gauge field to be positive definite, and this is the case for compact Lie algebras, but not for non-compact ones. The compact Lie algebra, turns out, is one which can be represented by Hermitian matrices. And this will be finite dimensional. So the generators TA will be Hermitian matrices for all representations R. Now let me make a remark. And the remark is that the factor of I in the Lie bracket 6.1, which is common in the physics literature, is there to ensure that the generators of compact Lie algebras are represented by Hermitian matrices at 6.4. This is common in physics. Whereas in maths, and also that's what Andreas did in the first term, one uses generators, let me call them T tilde A, which are related by the generators that I'm using by a factor of I. And these are anti-Hermitian. For compact Lie algebras. Which means that T tilde A dagger is equal to minus T tilde A. Now, in many cases, if you're interested in the physics of the problem, it's important to know, for instance, the energy is real or the action is real. And this is simpler to do if you work with physics conventions in which 6.4 holds. And that's the reason for the I in the Lie bracket in question 6.1. So let's stick with that convention going forward. But be aware that if you look at more mathematically oriented references in the literature, chances are that they will be using these other conventions in which the generators are anti-Hermitian for compact Lie algebra. Okay, next I'm making a claim, which is really the statement of a theorem that I will not get into. The statement is that a compact Lie algebra can be decomposed into the direct sum of U1 Lie algebras and of simple Lie algebras. This is a result due to Cartan. So in practice, our Lie algebra will be a direct sum of several U1 factors, say H of them, possibly H is 0, and then there might be several simple factors, G1 up to GL. Again, L might be any non-negative integer. Okay, let me remind you what the U1 Lie algebras and simple Lie algebras look like. And again, I'll always think of compact Lie algebras. Let's start with the U1 Lie algebra. Well, the U1 Lie algebra is the simplest non-trivial Lie algebra. It's the algebra which has a single generator T. And therefore, because the Lie bracket is antisymmetric, the Lie bracket of T with itself is 0. And so we call this abelian, meaning that it's commuting. And it's irreducible representations which I'll simply call irreps from now on, are one-dimensional, and they are specified by a charge, an integer, which is called a charge. So the generator will be equal to Q, where Q is called the charge. So we'll call this the charge Q representation of U1. And then this integer, if you want to be precise, multiplies the identity. Okay, so what about the simple Lie algebras? And again, we'll always think about a simple compact Lie algebras. Well, these have multiple generators, and we can define them by requiring that the structure constants f, a, b, c are non-vanishing, say, for all c. In fact, equivalently also or a or b. Okay, now let me give you an exercise. Well, this is the first part of exercise 9. I asked you to show that for a simple Lie algebra, the generators are traceless in any representation. So let me call the representation R. So I'll write trace TAR there is equal to 0. To prove that, you'll need to use the Lie bracket in 6.1 and 6.8. Then I claim, and please accept this claim, that there exists a basis of generators which we'll use from now on, such that we can take now the trace in a representation R, say of TA, TB, the product of two generators. In this basis, this trace of TA, TB is symmetric. And so by a change of basis, we can take it to be proportional to the identity matrix, delta AB. And the proportionality factor, C of R, depends on the representation. So here, trace R is the trace in the representation R of dimension R. So the same was true in 6.9. So this is a trace of R by R matrix. And C of R is called the quadratic invariant of the representation. Which turns out to be non-vanishing. A few remarks are in order now. The first remark has to do with the fact that we are free to normalize the generators as we wish. Indeed, we can rescale the generators TA, the structure constants FABC, and the quadratic invariant of all representations as follows. So we rescale TA by a factor of lambda, say where lambda is non-vanishing, and for us will be real. Then we also rescale the structure constant by the same non-vanishing constant lambda, and the quadratic Casimir by lambda squared. If we do this rescaling, then all the previous equations are invariant. So this is important to keep in mind. We have to specify our normalization. The second comment is that for the adjoint representation, which you have seen in the first term, I'll remind you what it is later today. Then equation 6.10, which involved the quadratic invariant, defines the so-called killing form, which is a symmetric bilinear form on the Lie algebra. So it takes two elements of the Lie algebra and it maps them to a real number. So the Killing form associates to two elements of the Lie algebra. Let's call them V and W. K of VW, which is the trace of the composition of the adjoint action of V with the adjoint action of W. And this, strictly speaking, is a trace in the adjoint representation, where here V can be expressed in the basis of generators as VATA, and same for W. And for compact Lie algebras, the Killing form is important because it's not only symmetric and bilinear, but it's also positive definite. So essentially it defines a metric on the Lie algebra. So if we go back to equation 6.10, here, it turns out that for the adjoint representation, in which case we're discussing the Killing form, but in fact for any other finite dimensional so-called unitary representation, this quadratic invariant here is positive, C of R. So then we can use delta AB, or more precisely, the Killing form, to lower and its inverse to raise Lie algebra indices. From now on, I'll just use delta AB. But if you want to be precise, you should probably use the Killing form. Anyway, they're related by a rescaling, and this normalization freedom in 6.11 essentially allows us to use delta AB. Since delta AB is the identity matrix, we can simply lower and raise indices with impunity. And now let me get to the second part of exercise 9. Exercise 9.2. Show that the structure constants lower, so that now they have all lower indices A, B, and C, is totally antisymmetric in its indices. Namely, if I swap A and B, I get a minus sign. And if I swap A and C, I also get a minus sign. And from this, you can get also what happens if you swap B and C. Okay, so far everything was about Lie algebras, compact Lie algebras, in fact. Now let's discuss Lie groups. You will remember from the first term that one can go from the Lie algebra G to the Lie group by the exponential map. And in fact, in this way, you don't get the full Lie group, you just get the component of the Lie group, which is connected, continuously connected to the identity. So let's say we have a Lie algebra element, let's call it alpha A TA, then the associated group element will be the exponential of I alpha A TA, where here alpha A are real because the Lie algebra is a real vector space. And for a compact Lie algebra, as I said, in any representation, TA are Hermitian, alpha A are real, and therefore G will be unitary. So compact Lie group, G is unitary, which is useful in physics, especially in quantum physics, because unitary transformations preserve probabilities. So note here that I use G both for the element of the Lie group and for the Lie algebra. Well, the two G's are hardly going to be distinguishable in my handwriting. I'll try to write something like this for the Lie algebra. and this for the group element. But hopefully it will be clear from the context which of the two I'm talking about, and when you look at the typewritten lecture notes, hopefully the distinction will be clear. And sometimes I will write that for the Lie algebra of the Lie group capital G, I'll write Lie of capital G, which will hopefully avoid confusion. Anyway, let's continue. So I reminded you what the representation of a Lie algebra is. Now, what about the Lie group? Well, by this exponential map applied now to the generators of a given representation, we can get from a representation of the Lie algebra to a representation of the Lie group. And in particular, in a R-dimensional representation R, the group element G acts as an R times R unitary matrix. So there will be an action of a group element on, say, phi, which is an element of the Lie algebra, and in a given basis, we can think of this as a R-dimensional column vector. And this will be mapped by G into G phi, where here I'm thinking of this notation simply as the abstract action of G on phi. And when I think of phi as this again is an R-dimensional column vector. So what is the transform G phi of phi under the action of the group G? Well, this is the representation of G, R of D. This is an R by R unitary matrix times phi, which is again an R-dimensional column vector, and here this is a matrix multiplication. Okay, there is an abstract action here on the left-hand side, and on the right-hand side, this is the actual action in practice by multiplication by matrix R of G. And then since the group element, the abstract group element can be expressed as an exponential of I times the Lie algebra element, the same is true in the representation. And so R of G as an R by R matrix can be expressed as an exponential of I alpha A times the generators dA in representation R. So this again is an R by R matrix, which acts by matrix multiplication on the vector phi. We can write all of this in components. In components, we have, say, jth component of phi gets mapped to R of G, which is an R by R matrix, has two indices, J and K, and the K index is contracted with the phi K. And this is, again, exponential I alpha A dA in representation R. This is a matrix, has indices J and K, which multiplies phi K, and repeat these indices K here are summed over. So sometimes I'll call this transformation by a group element the finite transformation. Of phi. And we go back to the Lie algebra from the action of the Lie group or the representation of the Lie group to a representation of the Lie algebra by focusing on infinitesimal transformations in which the parameters alpha A are infinitesimal. So for infinitesimal alpha, we get that phi is mapped to itself plus a small variation, which I'll call delta alpha, with the delta alpha, and I'll write it in components of phi j is equal to I alpha A, generator TA in representation R, matrix element JK times phi K. And we'll call this infinitesimal transformation or variation of phi. Next, I'll say more about representations, again, more abstractly. But first of all, I'll introduce the notion of a complex conjugate of a representation. So given a representation R, we can construct the complex conjugate representation R bar, which has as a representation matrix the complex conjugate of the representation of R. So now these two complex conjugation. Whereas on the left-hand side here is G in representation R bar. This is 6.17. So given a representation, we can complex conjugate it by complex conjugating the matrices which define the representation. Okay, now let me assign another exercise, which I think you will have seen already in the first term, but I want to make sure that we're all on the same page. This is exercise 10. It consists of a few parts. In part 1, I want to show that if phi transforms in an irreducible representation R, its complex conjugate phi star or phi bar transforms in the conjugate reducible representation R bar. This is very simple. You just need to use 6.17. So the second part of exercise, I'll ask you to show that as R times R matrices, the generators TA in the representation R bar are equal to minus the transpose of the generators TA in representation R. This is again a matter of using 6.17 and expressing R of G as an exponential of I alpha A TA in the appropriate representation. Finally, in part 3, let me introduce some notation first. So when I take a complex conjugation, denoted by star or bar, I will also lower the index. This is just notation. And then I construct the row vector phi dagger, which is phi complex conjugated and transposed. This has elements phi bar 1, phi bar R. And I want you to show that under the action of G, phi dagger phi, which is phi bar I, phi I, repeated indices are summed over, goes into phi dagger, R of G inverse, R of G times phi, which is the same as phi dagger phi. So phi dagger phi is invariant under the action of G. Next, a reminder of the adjoint representation, which I alluded to earlier when I made a remark about the killing form. So the adjoint representation which I'll denote as the adj, is the irrep specified by the generators TA in the joint representation, which are given up to a factor of I by the structure constant. So here, the adjoint representation will have a dimension equal to the dimension of the Lie algebra, G. And so the generator TA as a dim G times dim G square matrix will have two indices, say B and C, and this is what the generator looks like in the adjoint representation. And now an exercise about the adjoint representations. First of all, part one, check that 6.19 defines a representation of the Lie algebra. So you'll have to check that in the adjoint representation, the commutator of TA and TB is I, F, A, B, C, TC. So in part two, I ask you to connect the notion of adjoint representation in 6.19 with the adjoint action of the Lie algebra on itself that you will have encountered, I think, in the first term. The adjoint action of the Lie algebra on itself is defined as follows. We have for an element X of the Lie algebra, we have the adjoint action of X on the Lie algebra that takes a Lie algebra element and outputs another Lie algebra element. Let's say that the Lie algebra element is Y, then the adjoint action of X on Y is defined as the Lie bracket of X and Y. And I ask you to show that if we take the adjoint action of a generator TA on an algebra element, let me use algebra element Y, which is in a basis YB TB. And this is given by the generator TA in the adjoint representation that I wrote above in equation 6.9 here, with matrix element BC times YC TB. So in particular, this maps YB into TA BC YC. In other words, the adjoint action of the Lie algebra on itself simply implements the adjoint representation. And finally, in part three, I ask you to show that the quadratic invariant of the adjoint representation, C of the adjoint, is given by FABC, FABC, so the square of the structure constants with all indices contracted, divided by the dimension of the Lie algebra. Where here, Lie algebra indices are raised or lowered using delta, so the identity matrix. Finally, we have the last exercise for today, which is a reminder of term one, but also of linear algebra, which is about classical, so-called classical compact Lie groups. SUN, special unitary n by n matrices. SON, special orthogonal n by n matrices, and USP2N, which is unitary symplectic 2n by 2n matrices. Let me remind you what these groups are. So SUN is a groups of n by n complex matrices. I'll denote those as mat n of C. So this is n by n complex matrices, such that G dagger times G is n by n identity matrices that will define UN, or n by n unitary matrices. For special unitary, you also have the condition that the determinant of G is 1. There is a similar condition for SON. Now, these are n by n real matrices, such that G transpose G is the n by n identity. And finally, for the unitary symplectic matrices, which you might not have encountered before, G is now a 2n by 2n complex matrix, which is unitary. So G dagger G is the identity of size 2n. And symplectic means that G transpose times J, the so-called symplectic form, G is equal to J, where J symplectic form is following 2n by 2n antisymmetric matrix, which we obtain by taking blocks of the zero matrix and the identity matrix like this. And the first part of the exercise that I ask you to think about is to characterize the Lie algebras associated to these Lie groups, SUN, SON, USP, 2N, as vector spaces of matrices which obey certain conditions. So the exercise is to find which conditions these matrices should obey. Now, for the second part of the exercise, I need to introduce some definition. And the definition is that the fundamental or defining representation of a matrix group G, in particular, the special unitary, special orthogonal, and unitary symplectic group. This fundamental representation is the one in which the group G acts simply by matrix multiplication. So for instance, for SUN, G is an n by n matrix. It acts by matrix multiplication of a column vector of a dimension n. So we have phi, now it's mapped into G times phi, where now this is matrix multiplication. Or in terms of representation, the representation matrix RG is simply identified with the matrix G, which specifies the group element. And the notation will be that the fundamental representation will be denoted either by fund or say by n or 2n, where these are the dimensions. So it would be n for SUN and SON and 2n for USP2n. Okay, now that we have this definition, let me assign the last part of the exercise, which is to find the generators of the fundamental and its complex conjugate representation. fundamental bar for these classical groups, SUN, SON, USP to N. And show that the fundamental and the anti-fundamental representation are equivalent for SON and USP. Where equivalent simply means that they're related by similarity transformation. So you need to show that the generators TA in the anti-fundamental representation are equal to the generators TA in the fundamental representation up to a similarity transformation by some invertible matrix V. And if the Lie algebras are compact, as is the case for us, V will be unitary. So V inverse is equal to V dagger. That's all for today, so see you next time.